a lot of people in this class are attending this class today for the first time, since registrations were not completed by last week. So anyways, I did not cover any major thing as such in last week, except for just giving an example of what learning or machine learning is all about and what this deep learning class has, and some of this preparatory information which you need for the class. So today is when we formally start with what we would like to do in case of deep learning. So now, if you look into this whole field of deep learning, then majority of deep learning is where you would see the use of neural networks, or what we call as deep neural network. So DL is highly linked with use of deep neural networks. However, deep neural networks are not to be interpreted as being the only thing in deep learning. So there are several aspects of deep learning, and neural networks are just one of those aspects which are created over here. So this is just the model which is used for the learning, but there are different things which include the data over which you fit your model, and then there is a mechanism by which you fit your model, which is typically what is called as optimization. So there are these different aspects through which all of this deep learning can be taken into play. Now, to make it simple, let me give you an example of how we can start with it. So let us consider an example image. Now say this image has this number 1 written in this one. Okay. So this is my image, and let me denote this with a variable called as x. Okay. Just a minute. So now you have this image over here, which is called as x. Now this x is made out of a set of what we would call as pixels or elements present over here. So say this x or this image over here, this can be considered as an arrangement of multiple such scalar elements. Okay, and say that each of this has a certain value, which is x m comma n. Okay, or this can be written as x of m comma n in this particular figure, and say that in this particular matrix which I represent, there are m number of rows and there are n number of columns present over here. Okay. Now, if this is the scenario and say that x of m is real valued, in that case, you can write this as x is equal to this collection of x of m comma n for all m belongs to 1 to capital M and small n belongs to 1 to capital N. And you also see that this x can accordingly be written as belongs to R, or the set of real numbers, to the power of m cross n. So this belongs to a set of real numbers which forms a 2D triad. So it's essentially a tensor which I am representing. So in case whenever I write down that x belongs to r power of m cross n, the two critical information which you have is that x is real valued, every element of x is real valued, and it's a 2D tensor which is m cross n. Now, if this is the scenario, then and I have say these images which are of fixed sizes. So I have one of these image in which it is written as 1. There is another image in which it is written as 2. There may be another image in which also it is written as 2, and so on and so forth. It goes down, and there may be another image in which it is written as 0. Okay. So what I am doing over here is that say I have capital K such images. Okay. Now if I have capital K such images, and these images X can be of any of these classes. They can have any of these digits over here. Now first and foremost, what I do is I call this one as X1. So remember, whenever I put a bar underneath a particular variable, then this essentially denotes that this is a tensor of some sort. And tensor for us, so in a generalized way, we would look that all vectors, matrices, everything is a tensor. A tensor is a generalized representation for us, which is essentially a well guided and ordered representation of these numbers and nothing beyond it. Okay. So this thing can be called as x1, this I can call as x2, this I can call as x3. Like this, it keeps on going, and this one will be x of capital K. Okay. Now, corresponding to each of them, I will have some sort of a label which is given over here. So this label is another tensor which is called as y1. Over here, this can be a tensor which is called as y2. This can be a tensor which is called as y3. And I keep on going like this. And here I can have a tensor which is called as yk. Now let us look into what do we know about these xk's and yk's over here. So one is, what do I know about xk? So what is the nature of xk? Xk belongs to r power of m cross n. This is something which I know. Next is I have all of these yks. So what do I know about yk? Is the first question. So this is a set of images which represent any one number in the decimal number system. Now, if that is the scenario that each image essentially represents a number in the decimal numbering system, then how will this y look like? Okay. So what I can do is this y, I can represent this as some sort of another tensor constituting of certain elements. So I can write this as y0, y1 like this up to y of 9. Okay. So essentially, if you look over here, then this is a 9 element. There is a 10 element tensor. So y0, y1, y2, y3, y4, y5, y6, y7, y8, y9. This is what I have. Now, if this image x, so say I have this particular image x over here. Now, corresponding to that, what will be my y1 looking like? So if this is the situation, then y1 is going to have, this is 0, this is 1. So this one will be highlighted over here. So essentially, your y1 is going to look as a representation which is something like this: 0, 1, 0, 0, 0, then 0, 0, 0, 0, 0. Okay. Now say I had x2, which was like this. In that case, I will have y2, which looks like 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. This is what it will look like. So something which we know about y now is that this y belongs to a set of binary representations. So it can either be 0 or 1, and this will be a tensor which is 1 cross 10. So it has 1 row and 10 columns which is present over here. So this is something which I know about y. So what these things are called is something like this. So my image x, so this is say xk, has a corresponding which is called as yk. So this xk, this is my input. This one yk is my class label, or it can also be called as target. So from machine learning parlance, this can be called as target. In case of a classification problem, we would rather be calling this as the class label. So this is an image. Now, what I need to do is, what I want to achieve over here is I want to create a neural network in order to be able to solve this problem. Okay. Now, I can start by doing something like this. So what do I know? One is I know something about my input space. So every pixel will go as an input. Say each of these points is essentially a pixel over here. Okay. So what do I know about my pixels? So how many such values exist in my input?
M
into n. So it's mn number of values which exist over here. Input to a neural network. Now I need to get certain outputs over here. So what do I know about my number of outputs which will be present over here?
10.
There will be 10. Or in simple terms, I will write this as K. Capital, oh, sorry, no. There will be, let's use some value. See if I have some, okay, instead of writing it as 10 number of classes, if I denote this as capital omega. Okay. So capital omega is number of classes. In case of decimal system of digit classification, capital omega is equal to 10. So this is what I have. So now what I need to do is I need to be able to connect between these inputs and outputs. So how I do this connection is something like this. I take every single input and connect it with the output over here. and I also add another additional factor. Now, these inputs over here, they have a certain nomenclature. So we call this as x1, x2, x3, x4, or wait, instead of using these brackets, I will rather be writing it as subscripts over here to make it simpler. So what do we call them as? We call these as x1, x2, x3, x4, like this, and this last one is going to be x of m into n. This is what it is. Now similarly, these outputs over here can be written as y1, y2, y3 up to y of capital omega. Okay. So now, if this is the way in which I am writing it down, then how do I represent this one? So this link which I have connected over here, this particular link, this link has a certain weight or an importance which it assigns. Now this importance or weight is written as W1, 1. The second one link is written as W1, 2. The third is written as W1, 3. Then is written as W1, 4. Likewise, this one is written as W1, MN. Okay. So remember something. What I am doing is that the first subscript over here, the first index of the subscript is something which relates to the target point where it is connected to, and the second subscript is what denotes the source point from where I am connecting it. Now, if this is how we represent it, we can write down the end result in a algebraic form. So my y1 is equal to multiplication of some w1 comma j times x of j, where I am summing this over j is equal to 1 to m into n, m into n plus this term which we called as bias. So we call this as b1, say. Okay. Now this whole part can also be written as multiplication of two matrices. So I can have multiplication of what? So if my W is some sort of a row matrix. So this is called as W1. This is a row matrix multiplied by X, which is another column, which is a column matrix. So this is what do I do? This is mn cross 1, and this W is 1 cross mn, plus I add a bias over here, b1. Okay. Now from here, let us proceed to the next part. So next what I can have is, I have these same kind of inputs, x1, x2, x3, x4, so on and so forth, up to x of m into n. And then I am connecting them with y1, y2, like this, up to y of omega. Now comes that I want to connect my second neuron over here. So what I would do, change the color. So now I will be making another connection. This thing is now written as W2, 1, W2, 2, W2, 3, W2, 4. This becomes W2, Mn. And I have a bias which is B2. Now accordingly, I will be able to write down Y2 is equal to W2, J times x of j. This whole thing sum over j is equal to 1 to m into n and plus a bias B2. Okay. Now this whole thing can also be written as the multiplication of this row matrix. So row matrix is something which has multiple columns and just one single row. So 1 cross m n, this one multiplied by x, which is a column matrix. This is m n cross 1 plus b2. Now similarly, I can continue and then for any of my omega-th neuron, so say y of small omega, what can I write it down? I can write it down as w small omega comma j x j. J starts from 1 to m into n plus b of small omega. So this small omega belongs to 1 to capital omega. Now this whole thing can be now written as w of omega, which is of size 1 cross m into n times x, which is of m into n cross 1 plus b of omega. Okay. So let us review back what we had. So what we knew about this problem, where what we wanted to do was that given an image, you want to create some sort of a neural network, and I'm starting with a very simple neural network over here, which just has inputs connected down to outputs. And my objective over here is that you take in these inputs, then you multiply them with the weights, and you get your output coming over here. Okay.
Excuse me, sir.
Yes.
Sir, can you please explain what is a bias?
I will come to it. Just hold on.
Okay.
There is a purpose for the bias. I will come down to what is the purpose for the bias. So now one of the simplest way in which we could write this was a linear combination. Now in a linear combination, what I am doing is I have these weights over here. I'm assigning a different degree of importance to each of these inputs essentially over here. So what I'm saying is that every output is dependent on every input. Any given output is dependent on all the inputs over here, but with a varying degree. This is what I'm saying over here. Now, in order to assign what is that varying degree with which I can do it, so that degree can be associated with this weight W. Okay. Now that this degree of variation, which is associated with this W over here, the simplest linear combination can be, I can take a weighted summation as I see over here. Okay. Now remember something interestingly, say if all of these weights, these are non-zeros, and this x over here turns out to be all 0, then y will always be 0. Now in case I desire that this is not always 0, for some reason I just desire that my weight over here, that my output over here is not always 0, even if all of these x's are zeros. The only way I can achieve is through this bias. So this can shift it, give it a DC shift. So the purpose of this bias is essentially to still give this whole system a non-zero shift when all input given to this system is still 0. Otherwise, what will happen is that all zeros should be giving a firing up on one of these elements, say. Okay, but all others should essentially be 0. If I don't have this bias, then what will happen is each of them with this linear combination, irrespective of whatever weight is over here, all of them are going to give me 0 values. But that is not what I desired. I desired that any one of these omega, these y's over here should give me a non-zero value whenever it encounters all of these to be zeros. Maybe it should give a 1 in case it encounters everything to be 0. And for all other cases, there will be some other scenarios which will come down. So the only way I can achieve that is whenever I have this bias over here. So that's the reason why this is called as a bias. So it essentially shifts. The term bias comes from the point that it incorporates a DC bias or a fixed bias within a system of linear equations as we see over here. Okay, so now that I have written this one for the second neuron, and from there I go down to any of the generalized omega-th neuron, what I can write is pretty interesting. So now this whole thing can be rewritten as another interesting equation, which is something like this. So say I have all of these y's. So I found out for y1, I found out for y2, I found out for y3, or not y3. I found out for some generalized y of omega. Okay, and similarly I can go till y of capital omega. So how was I writing this equation for y1? This was getting written down as a multiplication of w1, which is a row matrix. So it has only one row and mn number of columns, multiplied by x, which was a column matrix, mn number of rows and one column, and there was a bias b1. Similarly, this thing was getting written like this. Okay. Now, this set of linear equations, what you can see is that all of these x's, they are the same, and each of these, so all of these x's, they are same, and each of these w's over here, they are row vectors. Okay, and independent. So now what I can classically do is I can rewrite this by stacking all of them. I can basically stack one row above the other row, and by that I will obtain this y, which now becomes a column vector of, so let me just write it as y, and this y is equal to w into x plus B. Okay, where this Y is a column vector, so that belongs to R power of, what do you have? You have one column, multiple rows. So you have this is omega number of rows cross 1. W over here belongs to what? So W is also a real numbered thing, which has now not just one row, but it has omega number of rows, omega cross m into n. X is the same thing, so this is R power of mn cross 1, and you have bias, which now becomes a column vector, which is again omega cross 1. So this is what you essentially know about this system of linear equation. So this effective representation is what we call as a single layer of a linear neural network. Also, in very simple terms, this is also known as a linear layer. Now, a linear layer does not necessarily mean that this is a linear system. It essentially signifies that this layer has a order 1 polynomial which is getting represented. Now, look into something. I started with a neural network which was supposed to be a graph-like structure, and essentially we see that the implementation of this graph-like structure is using just a matrix multiplication. So in essence, it looks something like this. X1, X2, X3, X4 up to X of M into N. Y1, Y2, Y of capital omega. So this side is what is called as input. This is what is called as output. Now this is a linear NN layer, and the mathematical operation of this one is written as y is equal to wx plus b. And just a minute. So now essentially what I have is, in this left hand side system, I have a graph like representation, and here I have a matrix representation. And what we knew about these y's are that this is a real numbered matrix of omega number of rows and only one column. W is also a real numbered matrix, but W is a square matrix. So this W is of omega cross m into n. Then what we know about X is that X is also real valued, and this is of size m into n cross 1. And then I know about B is that it's also a real valued matrix, which is of size omega cross 1. Okay. So are we clear till here?
Yes.
Okay. Now comes the next part, which is what is my objective? So say that, okay. So let Fnn be a function representing this neural network. So what I can write down is y is equal to Fnn of x. Okay, and this is equal to essentially wx plus b. Now the point is that what constitutes, now what do I want to achieve? So see, this is how I write it. So my objective over here is that we want to minimize some sort of a error between this prediction and whatever is the real over a set of examples. So what that means is something like this, that if I have a set of these things x1, y1, x2, y2. So this is a set of images, and then their corresponding some annotations in those y's which I have. And I said that I have k number of such. So xk, yk is what I have. Now this thing is what we call as the training data set. Now what we want to achieve is we want to define something which is called as an error. So how can we define this error? So say what I can do is I can find out something like E1, which is basically the difference between my prediction Y1 and my thing Y. This is from the first neuron. This is not from the first sample. Remember. Then I can find out E2, which is from Y2 and whatever is the real value of Y2. Like this, then I will be going up to omega only, which will be Y of omega, for which I am finding it out. Now, this thing can be an error which is found per neuron. But then I don't have some representation of the whole neural network's performance. So in order to do that, I can maybe use some way where this error E can be either summation of all of these E small omegas, or the other option can be I can have this E written down as the L2 norm between my prediction and my L2 norm of the difference between my prediction and my original, whatever is my target. Okay, so this is predicted and this is target. Okay.
So what is not?
Tell me.
What is L2 not?
Okay, L2 norm is basically your Euclidean distance. So L2 norm, this whole thing. Let me. So say I have this whole thing can be written as y1 1 whole square plus y2 minus y2 whole square plus like this up to y of omega minus y of omega whole square, and this taken half. So this is what it would be. Okay.
Sir, hello, sir.
Yeah.
Sir, like those x1, y1, x2, y2, those are individual data points, or like?
Yes. These are individual data points. So
Sir, like
this
what
is
order, sir? Like
a complete image and not the scalar value of a neuron.
so that's mn cross 1, like the order of it.
Yes.
Okay, so that's a complete data point of mn cross 1, like.
Yes.
Okay.
So remember something, in order to minimize this confusion, I'm going to use these bars. So if there is a bar below it, it essentially means that it is a tensor.
Sir, shouldn't we take mod in the error definition?
So if you want to take a L1 norm, just an absolute error, then you can take a mod.
I mean,
You just want to take, see, there can be different ways of defining error. There can be sum of absolute error. There can be sum of errors.
sir, but in the sum of errors, let us say if the class is, let us say, binary, let us like 1 or -1, we want to define.
You want to say in the sum of errors, it might be that the whole system's error is very high, but my sum of error can be 0.
Yeah, exactly.
Yes, that is pretty much possible. I'm just giving you an example over here. There are different ways of doing it.
Okay.
Okay, so tomorrow we will again start. Today it's end of the time. Tomorrow I will start from this error and then I will show you the remaining. Yeah, tell me.
A neural network is always linear, quadratic.
I will come to that proof. Don't worry, we have that proof. So till last year I did not do that proof, but this year I'm going to do that proof. I'm going to prove for for every single construct used within a deep neural network, whether it's a linear system or not, we will prove that.
Sir, could you share the Jamboard link so that we can have the
I will just put it up on the that table which we have on the course website.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir.
Thank you all then. We again meet tomorrow.
Thank you, sir.
Thank you, sir.